Today we're going to talk about making proofs that people can read. If you remember back to the early lectures, I mentioned the LCF architecture for a theorem prover, in which you had programming language, which was the original ML language, and you had your type of theorems as an abstract data type, and all the operations that produce theorems were ultimately code operating on that data type, so that the proof was literally a program. Now, when I say a proof was a program, incidentally, please don't imagine I'm talking about the proofs as programs paradigm you may have heard of. Sometimes you hear a confusion of that sort. This is nothing of the kind here. When I say a proof was a program here, I mean it was literally some code written in ML or a similar functional language that would call rules of inference through this data type and maybe calling lots of other code that could generate theorems. And that has got nothing to do with the proofs as programs paradigm that you may have heard of in type theory. Anyway, the trouble with such proofs is that they are just code and they're incredibly ugly and they're unreadable. The earliest attempt to make machine proofs that looked like mathematics was the Isar system developed in Poland, I think during the 70s. And it kind of developed in isolation there until maybe the 90s, when suddenly people in the West noticed it and said, hey, these guys have formalized a bunch of mathematics. And Isabel possibly has adopted the most from the Isar language. So Isabel has its Isar language. Now, of course, Isar sounds like Isar, but it's also named for the river that flows through Munich, which is where this stuff was done. Where instead of having just ordinary piles of code as the proof of your theorem, you have your own language which is trying to present mathematics in a kind of logical progression. It's typically more verbose than code, but it's infinitely easier to read. So that's what we'll look at today. And just to give another reason why, certainly if you want to convince a mathematician that what you're doing in this system makes any sense, a lot of mathematicians are skeptical of computers for a whole bunch of reasons, some rational, some irrational, and some even worry about a cosmic ray going through your computer and making it give you the wrong answer, which is kind of silly because A, that's extremely unlikely, and B, that would be picked up very easily if you just reran the thing. But mathematicians don't like being given an incomprehensible heap of stuff and then said, this proves that statement. They want to know why the statement is true. And indeed, all of us who are in the business of proving things should want to know the reason why a thing is true, and not merely that you gave this code to a system and the system said, oh, that theorem is true. So I have a little example here, and we're going to start by doing it the old-fashioned way. What am I showing? And by the way, it says at the top, the divides relation. So B divides A if and only if, the formula there. So if there's some factor, A is B times K. And of course, this makes sense for integers and natural numbers, for example. It makes sense, I guess, for rings. It's not very interesting for real numbers and so on. And what does the statement there say? It says, it's a very elementary fact, K divides N plus K if and only if K divides N. We've got a little blue thing there, and that is probably telling us that this thing is in the library already or could be proved automatically, but yeah, forget about that. So what do we do? The simplest thing you could ever do in such a case is say, oh well, let's unfold the definition. And remember, the definition is always called constant name underscore DEF for definition. So we unfold the definition of DVD, and we get a couple of ugly looking formulas. So that one there, the first subgoal, has an assumption. This variable Ka came from somewhere, and of course it's not a very pretty variable name. The other subgoal also has a locally bound variable called Ka and another bound variable called Kb, and all of it really looks incredibly ugly. Now the thing is, this is not difficult to prove, and one would be able to prove it anyway, and it wouldn't be very long, and probably we'd be fine. But it would be nicer to have a thing that you could actually read. So how do we do this? Well, first, sorry, I should address my bullet point there, which is slightly different. See, Isabel has a long history, and for about 20 years before the Isar language was introduced, you didn't have the stuff I'm about to show you, which meant if you had some subgoals like the ones on the previous slide, you needed to use tactics that would allow you to refer to this bound variable Ka and things of that sort. And so you could prove the theorem, but it would be ugly, and especially because bound variable names, they're not really significant. So you see a thing Ka, but if you change some definitions somewhere, it may happen that the next time you run it, it will have a different name, and then all your proofs will fail. So that's all, it's not very good. So what we will see is that through structured proofs, you can forget all those extra tactics, and you won't forget them because I'm not teaching you in the first place. So a lot of this stuff is not even in the course, although long, long ago when I used to teach Isabel in the 90s, I would have had to teach these things, so I don't teach them at all now. Instead, we use structured proofs, so you'll be able to set up these local contexts, the two sub-goals with their bound variables and their assumptions, to make them into local contexts in which you can refer to those things actually by their names, by names you can choose yourself. It will look clearer, and the proofs will also be more robust. So you will typically write more material because you will often be repeating things. So often you will be stating explicitly a sub-goal that was in fact calculated by the previous step. But it's a price worth paying because it means you can read the proof without having to run the actual theorem prover. So the ability to actually look over the proof and say, yes, he's doing that, then that follows, then that follows, therefore the conclusion. And that, of course, is how a mathematician reads proofs. So, this, why did I do it that way? Well, that's a bit clunky, but anyway. So this is the same example as before, only now it's a structured proof. I'm not going to tell you a lot in detail just now. We'll get to it through the lecture. But for now, I think the most important thing is, okay, so lemma statement. You can see the word proof, and you can see a bit of proof thing there that says simplify by DVD def, and then, God safe. I should apologize. I used to have auto there, and people say you should never put auto there, which is, I'm not sure I agree with that, but I was kind of half-heartedly complying with that instruction. Anyway, safe will break the thing down in a very simple way, kind of less powerfully than auto, into the various sub-goals, so that the original lemma statement divides into the same two statements that we saw in the, I guess, second slide, except instead of having 1 and 2 and these local variables, we have, so you see the first one, it says fix m, assume something, then we prove something else, and finally we show something else, and that something else is the thing which was needed for the first sub-goal. Then we have the keyword next, which is dividing the proofs of two separate sub-goals. Then we have fix m, so that's again introducing a local variable, and then we show the corresponding thing there. So some of the things that have happened, so those variables that were called Ka and Kb and so on, all I've done is here I said I don't like Ka, I'm going to call it m, and as long as I rename everything systematically I can call it anything I like. And instead of having to refer to assumptions by the assumption method or something like that, when I assume it there, it temporarily actually has the status of a theorem. So instead of having to use fancy tactics to do clever things with assumptions, this assume is just an identity, n plus k equals k times m. It's temporarily assumed, we do it whatever we want with it, and finally at the word next, it's gone. So that's all very beautiful. Now, this of course is the killer question. How do you write them? Well, that's what I'll cover in this lecture. Oh, by the way, just to interpret this slide, if you see where the cursor is, it's at, you see the cursor is just after the then have something. Now there's a lot of cool stuff. So the previous line assumed something. Now when you have then means give me the last thing that you got, the last thing you proved or assumed. So in this case, then is going to hand over the theorem from the previous line, that is n plus k equals km. Have allows you to state a new thing that you want to prove. This new thing is not the goal, not the final goal, but it's some stepping stone, some intermediate assertion you want to show. Or show is for the actual goals. I shouldn't have used the word show. An intermediate assertion that you want to demonstrate. So when you look there in the output panel, it says using this, so you can see the thing that is being piped in by then, and it also tells you the thing it's trying to show there, the immediate thing it's trying to show, which was given by have. Okay, and I've probably told all of this stuff already. Well, maybe not. Okay. A context is a crucial thing in Isabelle, particularly in Isar, and a context is a very simple thing. It's a finite number of variables, type variables, and a finite number of formulas, which you should regard as assumptions. So I have local variables, local assumptions, and within that context, I want to prove something. This is, I think, a very, very natural and general idea, and the ability that wherever you are, however deeply nested in your proof, you can take your environment and say, well, all those things that you think of as bound variables, you see, if they're bound variables, you suddenly get into a lot of technicalities about variable capture and so on, which makes our life difficult. If you just say, we're going to enter a new context in which all those variables, we're just going to regard them as variables, free variables. Turns out this very simple idea makes everything a lot simpler because there are no bound variables here anymore. Okay, so as I kind of hinted this already, you could see even in the previous example how using have, I introduced an intermediate result that then allowed me to finally reach the thing I wanted. Inductions also look very good here, but we will have a separate lecture on how you do inductions in the Isar language. So how do you start your proof? Well, the first thing you do is you type in the thing you want to prove, and then you need to know what you want to do next. So I thought I slightly cheated here using this safe, but typically you will have a first step that you will want to do. It may involve unfolding some definitions. By the way, the simp only is suppressing everything other than that particular definition. I suspect I did that because probably otherwise simplification would have solved the goal completely and that would have spoiled the example. And by the way, when you have a couple of things separated by commas, it just does them one after another. So if you like, in Isar, a comma is like a semicolon in any other language. It just does one after another after another. Okay, so you type that, and what you now see are the two sub-goals. And because you have those two sub-goals, you can already write the outer form of your proof. All I have done here is, in this case manually, it turns out there are pieces of code floating around that you can insert into your Isabelle session where you can click, and it will auto-generate a thing that looks like this, only it will generally be kind of ugly, but it's at least a start. But here I typed it all in manually. So for the first sub-goal, I said there's a bound variable, I'm going to call it m. There's an assumption, I'm just going to type it out. It had ka, so I'm going to type an m instead. And likewise, for the goal, write out your goal. Now the word sorry, it's a magic word, sorry. Sorry proves everything. Sorry says, I'm sorry, I don't feel like proving this. But Isabelle will record it as a theorem anyway. So we can pretend the first sub-goal is proved. Now we have next. I should probably be using my builds. Give me a moment. So yes, we name our bound variable. We make our assumption, and all of these were derived from the previous output panel that showed all those things. We copied out our conclusion manually. We put in dummy proofs. Now the word next is to separate the proofs of two independent goals. In particular, next will end the context. There are occasionally some clever people will try to, so when you have a lot of complicated contexts that actually turn out to be very similar for different goals, you can try to kind of layer them in the correct order and not use next, but you're probably showing off. Showing off can give you extra marks on the exercises as long as the showing off looks good. And I'm sorry, this is going to be subjective, and so you're kind of taking risks if you show off in the exercises, although maybe it's a good thing to do. Now the cool thing here, so there we've got the two sub-goals. As I said, I typed them out manually, although there are things you can get that can help you do this. Now, the funny thing is we have got a full proof. Well, I can't quite call it full because it's got two sorries in it. On the other hand, the full skeleton is there, and very often in a big development, you'll develop things this way. That is to say, let's say you're almost certain that where the first sorry is, you're almost certain it's true, but you'd rather not do it now. Why would that be? Typically, because the thing that you have for the sorry is a technical lemma. It will be hard to prove, and you're not quite certain whether that technical lemma is really going to help you prove the thing you really want to prove. So then what you do is you state your technical lemma, you assume the proof, you then continue on down using the technical lemma that you just assumed. Now, two things will happen. Either you'll discover the lemma was actually not of any use anyway, in which case you saved yourself a lot of work, or you find the lemma does help you, in which case you finish the second proof, then you go back and prove the lemma. This is kind of how top-down program design works in the same way, in fact. So often people will write their code in a very strange order in order that ultimately they have their whole system built. And often you have a thing, where you program using stubs where you can compile your system at any time, even though in fact the functionality, most of it is not yet there because your code is full of stubs. So sorry is very similar to this. So in a very big proof development, you may count your progress not by the number of things that you prove, because maybe you reached all the way to the end, but you have sorries in your proof, and then your job is to eliminate these sorries one after another. Okay, so our job now is to is to flesh out the skeleton, is to complete the proofs, to eliminate the sorries. And this is a typical thing. So what I've done here in the first one is decide that I need to prove something else. So I start with the assumption which I've called number 1, so you can give them names or numbers. What is this next one? Well, you see the thing we've got to show has got an existential quantifier, and it says, show me an m prime such that n equals k times m prime. And what we're doing with this intermediate thing is we're actually exhibiting the m prime and saying, well, let's try m minus 1. And it may be that that will be a very simple calculation because instead of a quantified variable, I've got an explicit term there. So that might be very easy to prove. And then as you can see, at this stage, I already used it. So I have already confirmed, see, BLAST is one of these automatic provers. I've already confirmed that the thing that I just wrote out and called 2 is sufficient to prove my goal. So now I feel justified in proving this statement 2. And by the way, yes, labels. And for this, I'm going to use sledgehammer. Have any of you used sledgehammer yet? No one has used sledgehammer yet. Proving theorems is hard. So what is very nice is that when you can point your cursor somewhere, open the sledgehammer panel, and then just click on the apply button, wait a few seconds, and then have lots of stuff come out, and that you can just click on one of those, and they will self-insert into your proof. So in this case, that intermediate result, although I probably could have proved it quite easily by the simplifier or something, people are lazy, and it's an awful lot nicer to simply click on your sledgehammer panel. I don't know why I inserted that particular proof, which is very ugly one. The last one, see the bottom line in the panel there, is a much shorter proof than the one there, which is referring to a whole bunch of stuff. But whatever. But you can choose any one of them. So yeah, sledgehammer did that. Oh, I see. I'm sorry, I misled you a moment ago. That sledgehammer panel is for the second one. There, so sledgehammer did both of those. And now that thing is finished. Is that a question?
Yes. So these labels, are they only necessary if you don't use them? Or so we have this keyword then before.
The labels, yes, the labels will all go away. I'll show you that. Yes, please don't use tons of labels. What I'm doing here is showing you the most basic approach. Every proof tends to need a few labels. But if you've got like dozens, then you're probably doing it wrong, and it does tend to get kind of ugly. One of the things I'm trying to show you here, of course, I'd like to show you sledgehammer, and there'll be a bit more on sledgehammer later. The ability to have stuff proved for you is, of course, cool, but it also works very nicely with structured proofs, where you see we started with a thing we didn't know how to prove, we broke it down. Now, it may well be that sledgehammer in this particular case could have even proved the original lemma, or could have proved those things without any intermediate steps there. But in general, you will have a thing that you don't know how to prove. Maybe sledgehammer also can't prove it, but you, with your intellect, which can see much further than any computer, will work out that, there's this formula here I should probably prove, which clearly follows from my assumptions, and which is obviously relevant to the result. So you type out that formula. If you're very lucky, sledgehammer will prove that formula for you. And then if you're super lucky, when you go down to your main goal, sledgehammer will then prove that with the help of the thing you just proved. So with structured proof, this kind of automation allows you to develop quite big proofs without even thinking very hard. The only danger there is that your proofs may become very long and very ugly, so what you should do at the end go away, congratulate yourself, I proved my theorem, go watch a movie, maybe come back tomorrow and look it over and say, could I maybe make it look a little nicer? It may be that it's got too much in it, it's maybe very ugly, and sometimes Sledgehammer outputs some really awful looking stuff, even though it runs. So you may want to try and beautify it a bit. Because remember, your proofs ideally should be intelligible, understandable, without the help of a computer to run them. They should be understandable just by reading them. Okay, now there was a question about labels, so we don't in fact need any labels at all. So we had 1 and 2, but you see then will refer to the previous line. So if we use then on both of those steps, we don't need either of those labels there. Maybe I shouldn't tell you about hence. You see, Macarius Wenzel, who invented the Isar language, he introduced hence as an abbreviation for then have, and then he decided he didn't like it. And then he wanted to ban it, but people were using it a lot. But maybe it's complicated for you because when you see then have, and it shows you the word then is in front of your eyes and you know that something is being piped in. Whereas certainly for an inexperienced user will have no idea what hence means. Likewise, then show. Again, you don't really need thus, although if you want to show off, I suppose you can. And there are, in fact, plenty of other things which I will get to later, and particularly about situations where you don't want just one thing, but a whole bunch of things that you prove in succession and then build up to prove some big thing with the help of 7 things you proved before. And then, even in that case, you can do it without any labels. This course is maybe wasted on many of you. Okay, so maybe I should continue from our Dilbert. So, this is another, I apologize for this rather silly looking example. It's not always that easy to cook up something that's interesting to prove. So this is a very arbitrary fact, but sometimes that's how it goes. Oh, by the way, so I don't believe you've seen the fixes, assumes, shows syntax before. It's quite convenient with Isar because certainly before they were introduced, you would typically write your lemma in the way we have seen in previous lectures, with the meta implies symbol. And then the first thing you would have to do is, in your proof, you would then have to assume those things, and the repetition of the assumptions is really quite tedious, and there's no need for it. So with these fixes, assumes, which then shows is now the statement of the lemma as you've already seen before, but if you use fixes or assumes, then you have to actually write the lemma statement after the word shows. And what it lets you do here is introduce your variable names, sorry, not bound variable names, they're free variables in fact. Give them the type as I've shown there, but you can also introduce assumptions of the theorem, and you can now refer to them directly without, you see, if, as I said before, if you stated your lemma with the fat arrow that we've seen before, you would then have to, in an additional step, assume that thing, and that would be boring. So we use this a lot, this way of stating theorems when you're in Isar. Now the thing we're actually trying to show is kind of dumb, so as you can see, we're working with integers. We're assuming that the absolute value of m times n is equal to 1, And now we're trying to show that the absolute value of m is equal to 1. And although this is a really contrived looking thing, very often in a real proof you may need to reason in this kind of way. And what we've done here, we now start putting together the proof. So I guess the argument, the reasoning kind of goes like this. So m can't be 0. How do we know m can't be 0? Well, it would violate the assumption, because how can m times n have an absolute value of 1 if m equals 0? So that proves that m is non-zero. And then the second line there is showing that it's not possible for the absolute value of m to be greater than or equal to 2. And of course, I've sorried that out, so I don't have a proof of that yet. But the two of them together should imply that the absolute value equals 1, and luckily Auto can do that. And actually, we're lucky that Auto can do that kind of linear arithmetic reasoning, because if you had to spout the details of that, it would actually could be rather tricky. Yeah, that follows. Now, what is this thing in purple? It is the little minus sign after proof, and I think I answered a question about this last time. So the minus sign means I'm going to do a structured proof. I can't think of any initial proof step to put there, so I'm going to put a minus sign which represents a no-op. Now, the interesting thing here is, okay, I probably could have proved this, this thing that had a sorry using sledgehammer, but I'm not going to do that this time. I'm going to try and write a proof manually. And this is where, and I think for a beginner, the way JEdit behaves, it seems a little weird. So you start typing the subproof that needs to go in there, and then it gives you a lot of error messages. I guess programming language IDEs might be like that sometimes, because now they parse your program right in front of you, and if you start typing in more code, it sees a lot of error messages until you finish the new thing that you were starting to type. Well, that's how it works here as well. So you type the word proof, and you got a lot of syntax errors because it isn't finished yet. And this is the thing. So I told you about the minus sign, which says do nothing. But if you type nothing, so that is the word proof, then Isar will ask if there is any default proof step lying around that matches the thing that you've just stated. And for negation, there is. So the default treatment of not P is to assume P with a goal of false. So when you type proof with nothing after it, it says write, assume 2 less than or equal to absolute value of m, and show false. Okay, and as I said, those are errors because we haven't finished it yet. So we have to finish it. So we still have a sorry, but now you see I put in our proof with no proof method, so it's going to assume the negated thing, and we have to show false. For the moment, it's just sorry, and that will complete it. So again, you see how this top-down proof development is, I hope, kind of satisfying, because although the theorem is not proved, you can feel that you're making progress, and certainly I, at least, and this is a subjective thing, but I certainly feel like I'm making progress when I see the proof developing in this way, and especially when the outer structure of the proof perhaps matches the argument that you see in the textbook. Okay, so there is the thing, the assumption, and that is the conclusion we're trying to prove. And in this case, I am not showing you how I thought of all of those things. You see, it's quite a lengthy proof that I have inserted here. I think the main thing, and what was going on there just very abstractly is I take the assumption that 2 is less than or equal to the absolute value of m. I derive various things. some of them are contradictory, then therefore false is proved. But really the main thing I suppose I want you to see here is that we can nest these proofs and we can nest them as deeply as we like. And you can have a proof, okay, this still fits, just about fits in a JEdit window, but you can have a structured proof that is thousands of lines long and it's not even unusual. Okay, now the next thing then is that the kind of reasoning we're doing here, I guess all of that is about 2 times the absolute value of n. So I guess that is the point, that the transformations in this proof are in fact that the left-hand side is staying the same, the right-hand side is changing, and that can be done using a thing called a calculation. But we need another break first. Right, I do hope you found that instructive. Okay, how do we do it as a calculation? So this is the same proof as before, that is starting from 2 less than or equal to absolute value of m, and now we want to get a contradiction. So what's happening here? So there we have 2 less than or equal to abs m at the top, and now the next line, I guess we've multiplied both sides by the absolute value of n. So you see the first step is trivial by monotonicity. Then the next line, you see we have dot 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 equals dot 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 equals. So we're always proving identity between the last right-hand side and the new right-hand side. So for example, abs m times abs n is equal to abs of their product. And then that turns out to be equal to 1 by the assumption we're given. And then combining those, so those 3 lines, the 2 of them joined with the dot dot dots there, is then a chain of, well, 1 inequality and 2 equalities, from which we then derive that 2 times the absolute value of n is less than or equal to 1, and that contradicts the assumption. Okay, now what I'm doing is walking through these calculations. So you see where the cursor is now, and you can see at the bottom what it's trying to prove, which is that thing about, oh, I hope you're not puzzled by the fact that I've written abs as ABS there, and it's got absolute value bars in the output there, but they're the same thing. So yes, the dot 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 referring to the previous right-hand side. Now the word finally, so the alsos try and combine adjacent steps, and the finally tries to combine all of them. Occasionally you'll get a weird message if something isn't right, but if you've done it right, you see it. What we have proved from all of that is 2 times the absolute value of n is equal to 1. So this calculation should appear, there's a calculation output there, should appear in your output buffer. And finally, the dot is another kind of pseudo-proof. So the dot basically, you kind of wonder why, what was Macarius Wenzel thinking when he invented this? So the minus sign means a no-op, and the dot means, I'm not exactly sure, I guess the dot means I proved it already, dummy, because this dot is merely recognizing that the thing piped into the have by the finally, that is, the dot is confirming that the calculation you've just done in the previous 4 lines is identical to the thing shown there. So when it's identical, you can just type dot. Sometimes you will see that it's not in fact identical, but it's a trivial consequence from it. You can put by simp or by auto or something to finish it off. Question?
I've once seen two dots.
Oh, two dots is the default rule. So two dots, so when you have proof with nothing, I am 99% sure you could write proof with two dots instead, and I believe they are completely synonymous. Please don't do that. Okay. It's not a bad language, but it has its quirks. Okay. So there I said, oh, by the way, less than or equal is built in, greater than or equal is available to you, but greater than or equal is kind of a macro that expands into less than or equal. And that means if you use greater than or equal in these calculations, things will go horribly wrong because it will think that the left-hand side is actually the right-hand side. So please never use greater than or equal here. You can, however, so not only use the built-in things like equals and less than, you can also introduce your own. So if you have your own favorite relation, whether it's a divides relation or some completely new relation that is needed in your work, it is possible to declare it as a transitive relation so that you can do these calculations. Okay, now what do these look like? Well, you start with have. You have your also haves. Oh, this is not quite right. So you will have the three dots, referring to the previous right-hand side. You do not have to have equals. You could have other relations there. Finally, combines all the previous steps. For some reason, it goes crazy if you have a step of the form E equals E. It is the same thing. So I think it expects you won't do that. Of course, you won't ever do that deliberately, but it's actually quite easy to do that by accident if you've got complicated expressions. So if you have something that also have E equals E, finally tends to give you a weird error, which is unfortunate. And then, yes, you might restate the whole calculation and use a dot, or you might state something new. And that is the end.